Once more, last time we were able to solve a system of linear equation using the method of Gauss-Jordan as well as the Gaussian elimination. Now we are ready to solve real-life problems, and we are going to apply what we learned last time in solving the system of linear equation. So lesson 1.3 is about applications of systems of linear equations. The objectives for today: set up and solve a system of equations to fit a polynomial function to set of data points, and set up and also solve a system of equation to represent a network. Systems of linear equations arise in a wide variety of applications. In this section, you will look at two applications. The first application shows how to fit a polynomial function to set of data points in the plane. And the second application focuses on networks and Kirchhoff's laws for electricity. First, we deal with polynomial curve fitting. Let us consider endpoints in the xy plane. So we will have here a set of ordered pairs x sub 1, y sub 1, x sub 2, y sub 2, up to x sub n, y sub n, which all represent a collection of data, and you want to find a polynomial function of degree n minus 1, such that we will have your p of x is equal to a naught plus a sub 1x plus a sub 2x squared plus dot 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 plus a sub n minus 1 times x raised to n minus 1, whose graph passes through the points. This procedure is called the polynomial curve fitting. When all x coordinates of the points are distinct, there is precisely one polynomial function of degree n minus 1 or less that fits the n number of points as shown in figure 1.3. So we see here that we're given several points with different x coordinates. We have here x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3, and x sub n, y sub n. Now, how do we find the best fit for a given set of points? Example, determine the polynomial p of x, which is equal to a naught plus a sub 1x plus a sub 2x squared, whose graph passes through the points 1, 4, 2, 0, and 3, 12. So what we need to do is simply substitute, say, the value of x and y into the particular equation. So for example, p of 1, okay, when x is equivalent to 1, we will have p of 1 is equivalent to a naught plus, you will have here a sub 1 times x, which is 1, plus a sub 2 times 1 squared. So we will have a naught plus a1 plus a sub 2, which is equivalent to your p of 1, the function, which is equivalent to 4. And then doing the same thing, we will have x is equivalent to 2, so that we will have a naught plus, you have here 2a sub 1 plus 4a sub 2, which is equivalent to 0. And then we will have a naught, that is p of 3 is equivalent to a naught plus 3a sub 1 plus 9a sub 2, which is equivalent to 12. Now we will have the system of a linear equation, 3 unknowns in 3 equations. So we already were able to set up the system of equation, and all we need to do is to solve it using Gauss-Jordan elimination. So again, you can simply form the augmented form of the matrix, which will be, okay, do we have that one in the next slide? Let us see. So if we are going to find the augmented form of the matrix, what do we have? Can I write it here? So say Since we already set up the system of equation, the augmented matrix is given by 1, 1, 1. And then we will have a 1, 2, 3. And then we will have your 1, 4, 9. And the constant terms being 4, 0, and 12. By applying the elementary row operation and converting this augmented matrix into reduced row echelon form, we'll be able to find that the solution A0 will be equivalent to 24, A1 to be negative 28, and A sub 2 to be equivalent to 8. And then substituting it into the model, we will have P of X is equal to 24 minus 28X plus 8X squared. Now let us try to apply this concept of polynomial curve fitting in the next example. Okay, so by the way, this is the graph. So we will have a quadratic function given by this parabola. So this is another application of curve fitting. Find a polynomial that relates the periods of the 3 planets that are closest to the sun to their mean distances from the sun as shown in the table. Then use the polynomial to calculate the period of Mars and compare it to the value shown in the table. So we have here the mean distances are in astronomical units and the periods are in years. So we're given the mean distance as well as the period. So let's say the mean distance will act as our independent variable, and let's say period will be our dependent variable, and we will have several ordered pairs. That means when the mean distance is 0.387, the period is 0.241, referring to the planet Mercury. And for Venus, we will have the mean distance from the sun of about 0.723, and the period will be 0.615, and for the Earth, that will be 1 and 1, and for Mars, that will be 1.524 and 1.881. So we can consider the set, we can consider the following as simply ordered pairs. So by, again, applying the same procedure, just like what we did earlier, we say the model will be a quadratic polynomial function. P of X is equal to A0 plus A sub 1X plus A sub 2X squared. So we only need to satisfy this function by the given value of X and Y. So say P at 0.387. So here P at 0.387 is equivalent to A0 plus 0.387 of X, 0.387 of A sub 1, and then we will have plus 0.387 square times A sub 2. So we have this one is equivalent to 0.241, and with 0.723 and 0.615, we will have the equation A0 plus 0.723 A sub 1 plus 0.723 square times A sub 2 equivalent to 0.615. And then finally, with the last point being 1 and 1, we simply have A0 plus A1 plus A2 equals 1. So with this given system of equation, all we need to do is to form the augmented form of the matrix and apply your Gaussian elimination with back substitution, or simply proceed with Gauss-Jordan elimination to come up with the reduced row echelon form of the matrix. So the solution is as follows. We'll have A0 to be about negative 0.0634, A1 to be 0.6119, and A sub 2 to be 0.4515. Substitute this into the polynomial function, and you will have this particular equation. Now, if we have P of X equivalent to negative 0.0634 plus 0.6119x plus 0.4515x squared, and let's say we want to find the value of the function when x is equivalent to 1.524, we only need to replace x by 1.524 as well as for x squared as 1.524 squared. So we'll be able to use this particular function to predict the value of the period for a given value of the mean distance. Now that will be equivalent to 1.918 years. Okay, so we can actually find the graph and we see the following. We have your Mercury, which is of course closest to the sun, followed by Venus, and then Earth, and then Mars. Note that the period of Mars, which is shown in the table as 1.881 years. The figure below provides a graphical comparison of the polynomial function to the values that are shown in the table. Okay, so we are actually trying to compare the result of the model, okay, with the actual values.